Hi, welcome to the channel Too Irrational. I'm Pranay Sharma, and in this video we are going to see the solutions of CS1 Paper B conducted by IFoA Institute in September 2024. We are going to go through the complete solutions in detail, but if you want the solution sheet, I would leave a number below where you should WhatsApp or Telegram your email ID and ask for CS1 solutions, and we are going to email you the same. Without any delay, let's get started. Question number 1. For an investigation into the buying behavior of consumers shopping at an online store, data about the age, time per month spent on the online shop's website, and the number of purchases from the shop per year are recorded. This dataset is saved in the file onlineshop.rdata. After loading the data into R using the command the data frame online shop will be available. The data frame online shop contains the following three variables: age, time spent on the website, purchase per year. Okay, so these are the three variables that we'll see. First is fit the generalized linear model to the data assuming a Poisson distribution with a log link function using purchases per year as the response variable and the age and time spent on website as explanatory variable without an interaction term. Your answer should include the estimate coefficients, the deviance, and the IFoA information criteria of the fitted model. To load the data, first thing we'll make sure is the environment is empty. Then we'll go to that file, right click, open with RStudio. Yes, here's our data. You can see age, time spent on website, and purchases per year. So then question 1, first part, we are supposed to create a GLM. I'll name it as model 1 is GLM. While writing the formula, make sure that the spellings are right. Data is online shop and family is Poisson. We don't need to specify the link function because log is the default link function. They had asked us to show the coefficients, the deviation, and the AIC number. So if I just run the model, you will see that we have all those values. We have the coefficients, we have the deviance, and we have the AIC number. So I'll copy this and paste it as an answer. I'll put hashtag. So if I press Ctrl Shift C, it will make it as a comment so that it is not mistaken as a command. Second part, state an expression for the expected number of purchases per year in terms of the variable age and time spent on website using the fitted model in part 1. So for the second part, we'll just say y is equal to exp because the function was log a plus b1 into x1 plus b2 into x2. Now we'll have to label them properly. So y is the expected number of purchases from the shop per year. A is the intercept parameter. B is the slope parameter for age of the customers. X1 is the age of the customers. B2 is the slope parameter for the time per month spent on the shop's website. And X2 is the time per month spent on the shop's website. It is suggested that the log link function may not be appropriate and a square root link function should be used instead. That is, g mu is equals to root of mu. In R, a square root link function can be specified using family. See, instead of link log, we can write link sqrt. Fit a GLM on data assuming a Poisson distribution with a square root link function using purchase per year as response variable and age and time spent on website as explanatory variable without an interaction term. Your answer should include the estimated coefficients the deviance and the AIC of the fitted model. So we want the same thing, so I'll copy. Instead of model 1, I'll write it model 2, and here in family we have to specify link is sqrt. Now we again want all of these values, so model 2, we have these values. Again I'll copy it as answer, paste it here and make it into a comment using Ctrl+Shift+C. Fourth part, state the expression for the expected number of purchases per year in terms of the variable age, time spent on website using the fitted model in part 3. And fifth part, compare the model in part 1 and 3 and decide which model should be preferred using the deviance. What I can do is I can just copy this second part, paste it here, and instead of exp we'll have raised to 2. Everything else is exactly same. In fifth part we have to compare them using the deviance. So if you compare the both the models, the degree of freedom are going to be exactly same. You can see here degree of freedoms are same. So you can compare directly the deviance because AIC would be lower for the one that has the lower deviance. So clearly the first model has lower deviance, and you might also observe their AIC number is also lower. So that is what we'll mention. As the degree of freedom are same for both models, the model with the lower deviance will be better model. So model with log link function is a better model. It is suggested that the deviance is not an appropriate measure to compare the two models in part 1 and 3, and the AIC should be used instead. Comment on this suggestion in the context of comparing the two models in part 1 and 3. In particular, identify any advantage that the AIC may have compared to the deviance in this context. For comparing two models, AIC number should be used. AIC number considers the deviance and the number of parameters, that is degree of freedom, and is a better measure than just comparing the deviances, as it considers the complexity of the model too. But in part 1 and 3, the number of parameters, that is the degree of freedom, are same. Hence, there is no advantage in considering AIC over deviance. Let's go to the next question. Question number 2. An investment analyst is interested in the relationship between the share price of a company and its earning per share (EPS). A sample of the data of 8 companies has been collected. This is stored in the file of company sample.rdata. After loading this data into R, the data frame company sample will be available that contains 2 columns. Price, that is the company's share price, and EPS, the company's earning per share. Fit a linear model to the sample with the price as the dependent variable and EPS as the independent variable, and state the estimated coefficients of the model. So the first thing before loading the data is make sure that there is nothing present in here. So I will clear the global environment, then go to the file. So this is the file that we want, company samples. Right click, open with RStudio, and yes, so this is the data. We have 8 observation of 2 variables. So we have to fit a linear model. I will write it as model 1 is equals to LM in bracket. Our price is the explanatory variable and EPS is the dependent variable. Data is company samples. That's it. I'll press Ctrl Enter. Here's our model. Now we want to show the coefficients. I'll say model 1 dollar coefficients. So these are the coefficients. I'll write it them as answers. Let's go to part 2. State the value of the coefficient of determination R square for the model fitted in part 1. So we want coefficient of determination. For that, first I will need the summary. So I'll say SUMM1 is summary of model 1, and using that summary I can show the coefficient of determination R squared, that is 0.0953. So it's a very small coefficient of determination. Third part, perform an analysis of variance using the ANOVA command to test if there is a linear relationship between price and EPS. Your answer should include the F statistic and the p-value of the test. So we can use the ANOVA command and give the model 1. So you can see it already contains the F value and P value. If you just show this table, that is fine, but I prefer to write it in test 1, store here, and then I'll say test $1 F value, that would be this, and test $1 P value, that is this. Fourth part, comment on how well the linear model in part 1 fits the data using your answer to part 2 and 3. So we'll comment the R square value is 0.09538, which suggests that only 9.54% of the data is explained by the model, hence no linear relationship. The p-value of the ANOVA test is 0.4567, which is significantly higher than 5%. Hence, there is no linear relationship between the two variables. Both second and third suggest no linear relationship. The analyst believes that the observation where price is equal to 99 is an anomaly because of the large size of the value of the price and should be removed from the sample. Fit a linear model of the sample without the observation price is equal to 99 and state the value of R square. They have given you even the hint how to remove the row. So you can see here from the data that we have price 99, that is the fourth row. So you can directly remove the fourth row, or if you don't want to assume that the fourth row is only going to be the one, I will create company sample 2, that would be company sample such that company sample dollar price, that means price is not equal to 99, comma, all columns. So the row is going to be such that company sample price is not equal to 99. So now when I see this second one, you can see I do not have any row that has company sample price as 99. So the fourth row has been removed. I'll create a model. Say model 2 is linear model. Price follows EPS such that data is company samples 2. We want to show the R square, so I will create the summary for this as well. SUMM2 $R squared. So the R square value is this. Now you can see it is 84%, clearly very high compared to what we had before. In 6th part, compare the fit of the model from part 1 and 5, and 7th part, discuss if removing the observation where price is equal to 99 is appropriate. So in the 6th part, the R squared value improved significantly after removing the row where the price was 99. 84.63% of the data is explained by model 2, hence the linear model is a good fit after removal of the value. Now we have to justify that this price is equal to 99 should be removed. So for that, residual versus fitted plot would be a very good way of doing it. So I'll say plot model 1, and I think the first one is going to be the residual versus fitted plot. Here we go, and you can clearly see here this is the model and this is the fourth value. So fourth value is an outlier. We can show that from this residual versus fitted plot. So we'll say from the above plot we can see clearly that the fourth value is an outlier. Hence the observation of the price equal to 99 should be removed. Let's go to the next question. Question number 3. A random variable x with the value in the interval of 0, 1 has a following cumulative distribution function, and the inverse CDF is this, where a is greater than 0 and b is greater than 0 are the parameters. The probability density function is then given by this. You do not need to check the form of the inverse CDF or the PDF. Plot the inverse CDF f inverse u for an appropriate range of the value of u, where a is 0.7 and b is 0.5. So the first thing you should always do is clear everything from the previous question before you start a new question. So question 3, first part. A is 0.7, b is 0.5, and I will be using the curve function to create the plot. You can always use the lines function, you can use the plot function by creating the x coordinates and the y coordinates. So this is the function 1 minus u raised to 1 by b raised to 1 by a. Now instead of u I will write x because I have to give it as an expression here in curve. So I'll say curve 1 minus bracket 1 minus x bracket raised to bracket 1 by b, and then this raised to 1 by a. These are the values. Now for x I will have the values of 0 to 1. I run this. This is the function that we are talking about. Now let's label it properly. So I have named the main title inverse CDF. Here these are the u values and we have inverse CDF here. Second part, simulate 1000 values of x for a is equals to 0.7 and b is equals to 0.5 using the inverse transformation method, and store the 1000 simulated values in the vector R for later use. You must use the command set.seed123 to initiate the random number generator before you start the simulation. So we'll start with the set.seed as 123. Then let's say u values will come from uniform distribution, so random sample from uniform. We want 1000 values with the parameters 0, 1, and the x values will just be this formula here, but instead of x here I would need u for the values of u. Third part, plot a histogram of 1000 simulated values obtained in part 2 using the relative frequencies. Relative frequencies just means probabilities. Plot the PDF of x for a is equals to 0.7, b is equals to 0.5 for the values of x belonging to 0, 1. The graph of the PDF should be superimposed on the histogram produced in part 3. This again should tell you that here we need graph of probabilities because we can only superimpose on the probability graph or the density graph. So first the histogram for the values of x, we want probability equal to true. This is the histogram that we want. I label it properly. For superimposing, I will be using the curve function again. So curve. Now the PDF will come from the question Here we have the PDF a into b x raised to a minus 1, 1 minus x raised to a raised to b minus 1. So a into b into x raised to bracket a minus 1, then into bracket 1 minus x bracket actually x raised to a, then bracket raised to bracket b minus 1. This is the function. I lost a closing bracket. You have to make sure that all the brackets are written properly. Now I want to add this true, add to the existing one. I want to change the color to, let's say, red, and that's it. Press Ctrl Enter, and here you can see the graph fits the existing data properly. Fifth part, comment on the plot in part 4 comparing the simulated values of x with the PDF, also taking into account the size of the simulated sample. The curve fits very well in the plot of the simulated values as the sample size is large and the fit is well. Hence the simulated value generated by the inverse transformation method must follow the distribution of x. Sixth part, plot the PDF of x for a is equals to 0.7, b is equals to 0.5 for the values of x belonging to 0, 1 in a new plot, and add the PDF of a is equals to 3, b is equals to 2 to the same plot. So first let's note down these new values. So I'll say a2 is equals to 3 and b2 is equals to 2. I'll use again curve to run the expression. Now we want the expression of this PDF. Want this, and for the values of 0, 1, that is what our values of x are going to be. Let me run and see. Yes, this is the plot that we would like, and let's change the color to red, and let's change the y label as density. Run this. This is the graph that we want. Now we want to add the graph of this a2 and b2. So again I will paste this function, and wherever I have a I will write a2, wherever I have b I will write b2, and I would say comma, add equal to true, change the color let's say is blue, and run this. You can see this blue line is going below this. So let's start the density from 0, go till let's say 4.5. So I will change that in the original curve. I'll say y limit must be equal to a vector starting from 0 and going till 4.5. So here's the original graph. Now I will add. Here you can see now the complete graph properly. A statistician wants to use one of the PDFs in part 6 as the prior density for a Bayesian analysis. Comment on the prior belief about the underlying parameters that the two PDFs represent. For Bayesian analysis, the choice of the prior distribution depends on the shape of the PDF. A 0.7, B 0.5, it should be used where the prior belief about X is that it is evenly spread throughout except at the extremes where they have higher density. A3 and B2, it should be used where prior belief about X is that it is negatively skewed with the mode around 0.7. That is what I have assumed, that mode is somewhere here around 0.7, or maybe you can say 7.5. Seems more closer to 0.75. So let's write that. Let's go to the next question. Question number 4. Two members of an interview panel have scored a large number of applicants with the purpose of ranking the applicants according to their suitability for a job position. The scores for a sample of 12 applicants are given below, with SA and SB denoting the scores of interview panel members A and B. So we can copy this. Plot a suitable graph for assessing the agreement in the two panel member scores. Second part, comment on the agreement in the two panel member scores based on the plot in part 1. So again, let's just clear everything from question 3 and we'll paste the data here, run them. Let's make a plot. This seems fine. Let's label it properly. So here it is. Now it would always be better if we have the line to compare it with. So I'll create a linear model. Although this is not necessary, but it is always easier for us if we have that line. I'll have the color red for that line. Then the comment, there seems to be an moderate positive linear relationship. The two panel members' scores are in agreement. Third part, calculate Pearson's correlation coefficient R for these data, calculate Spearman's rank correlation RS for this data, and calculate Kendall's rank correlation coefficient tau for these data. Comment on the suitability of the three correlation coefficient used in part 3 to 5 with respect to the purpose of the scoring. So first we want Pearson's. It's just COR and we'll give both these values and we are getting 0.75. Then for Spearman we have the same COR SA comma SB, but then method is going to be S. S for Spearman, you can write the complete Spearman or you can just write S, that works. Copy and paste it as an answer, and then Kendall's. Same thing, COR SA comma SB, and the method is going to be equal to K, written in inverted commas. So here we get Kendall's rank correlation. For the comment, as the actual scores are to be compared, Pearson's correlation coefficient is a better measure of the correlation. The Spearman's and the Kendall's correlation uses the rank of the scores instead of the actual scores. Hence, they give an approximate relationship. Seventh part, perform the three statistical tests for the suitable hypothesis of no association between the scores of the two panel members using one of the correlation coefficients in part 3 to 5 for each test. For each test, your answer should include the p-value and a conclusion. Comment on the validity of the test in part 7 for testing the hypothesis of no association between the scores of the two panel members. So first, let's do Pearson's test. So we'll just say test 1 is cor.test and again SA comma SB. We do not have to change anything or mention anything here. Next, we want the p-value. So test $1 p-value. Here it is. Clearly it is less than even 1%. You can comment according to 5% or you can comment it according to 1%. At 5% level, we have sufficient evidence to reject H0. The Pearson's correlation coefficient is not 0. Hence, there is an association between the scores of the two panel members. We have to do the same thing for Spearman and Kendall. So p-value is less than 5%, so we are rejecting it at 5%. So instead of Pearson's, now I want Spearman here. The rest remains exactly same, and I think that is what we'll get in Kendall as well. Yes, p-value here is around 2%. So again, at 5%, we reject H0. We just change the Spearman to Kendall. For the 8th part, the Pearson's test assumes a linear relationship and normally distributed data. The test is valid for this case. The Spearman's and the Kendall's test do not assume normality but are more suitable for ranking or ordinal data. These tests are not valid for this case. Let's go to the last question. Question number 5. A sample of 100 daily sales amount at the store is collected with the aim to investigate if daily sales amount are affected by whether or not the store has a substantial discount offer available on a particular day. The data are available in the files sales_data.rdata, which contains the following variables for 100 days. Sales.amount, the daily sales amount, and the discount, an indicator showing whether or not the store has substantial discount offers available on each day. That is discount equal to 1 if discounts are available and discount is equal to 0 otherwise. So this is a factor. Discount is a factor. First part, plot appropriate box plot for comparing the sales amount on discount and non-discount days. They have given you a hint. You may find the box plot formula, whatever R command useful. So for the first part, we can use the formula first. We'll have to load the data. I'll clear this. We'll go to the data, right click, open with RStudio, and yes. So here we have the discount and the sales amount data. Now we can make a box plot with box plot sales.amount follows discount. You can make it like this. Here we go. You can give the names properly to this 0 and 1. So here we have without discount and this is with discount. Now there are many different methods to do this. I'll show you, let's say, one more where you could have separated the data. So let's say sales WD, that means without discount, is going to be sales.amount where discount double equal to 0. So this will give me without discount. Sales with discount, let's say sales.amount where discount double equal to 1, and then you can make a box plot out of it. And when I press Ctrl Enter, here you can see I have the box plot. We will have to label it properly. So again, I can put the names, and yeah, that works. And I can also put the main label, amount of sales, and I will put this main label also here. So both will look exactly the same. This was from the above, and here when I run this, you can see the same thing. You can put X label and Y label if you want to, but anyways, it's fine. Let's go to the second part. Second, comment on the effect of the discount offered on sale amount using the box plot produced in part 1. From this box plot, you can see all of these values with discount is higher. So this is going to be Q3, this is median, and this is going to be Q1. So each one of these values is higher for with discount than without discount. That is what we have mentioned here. From the box plot, every quantile of the sale with discount is more than that of the sale without discount. Hence, the discount increases the sale amount. A sale analyst considers two distributional assumptions, a normal and a gamma model for the daily sale amount. Fit two separate generalized linear model to the data, one for each of the two distribution assumptions, to investigate the dependence of the daily sale amount on availability of the substantial discount offer on the day. For each model, you should use canonical link function. So first, let's say we are creating normal distribution. Okay, normal distribution model. Let's say model 1 is GLM. Sales amount follows discount, but discount should be a factor because here discount is just a numerical value. So we'll have to create factor discount. You can always create a separate data frame for this discount and sales amount and use it here, but this will also work. I'll just say family is equals to Gaussian. Now for gamma, we have exactly the same thing, just the family changes. So I'll say model 2, and instead of Gaussian, I'll have gamma with capital G. Then fourth part, comment on the impact of the availability of substantial discount offers on daily sale amount based on the output of the two models fitted in part 3. Your answer should include the relevant p-value and the interpretation of the estimate of the coefficients of discount variable for each fitted model. So we'll get the p-value in the summary. So SUMM1 is summary of model 1, then SUMM1 dollar coefficients. We don't actually need the whole coefficients, we just need this p-value. So I will just take second row and fourth value, that's it. I don't need the whole of the coefficients. So paste it here. Now we need to comment on it. As the p-value is low, there is a significant increase in sale amount with the availability of discount. This was for normal distribution, so I will just write here normal distribution model. And next we want for gamma distribution model the same thing. So summary, I will write it as summary 2, summary model 2, and again from summary 2 I want the coefficients. I'll run this, and this is the p-value, and p-value is very small. I will just copy paste the same comment and paste it here. Fifth part, determine which of the two model fitted in part 3 should be preferred for investigating the dependence of the daily sale amount on the availability of substantial discount offers on the day. So we can just compare their AIC number. So let's say I will make a vector model $1 AIC comma model $2 AIC. So here are the AIC numbers, And we can see that the AIC of model 2 is lower than the AIC of model 1. So model 2 is better. We'll comment that. Sixth part, determine the expected sales amount on a discount day under each of the GLM fitted in part 3 explicitly using the estimated coefficients from each model. So they have specifically said that we have to use the coefficients from each model. That means we cannot use the predict function. For normal distribution, we'll just have model 1 dollar coefficients. First I will choose the first coefficient, that is our alpha, and then beta. So model 1 dollar coefficient 2. Because it is a factor, that is why this will just take the value of beta. If we had no discount, I would not take this coefficient 2. I would have just taken coefficient 1. So then gamma. For gamma distribution, we'll do the same thing, but the link function for gamma distribution is inverse. So I'll have 1 upon this model 2 dollar coefficients first plus model 2 dollar coefficients 2. So you can see we have basically the same answer. That's the expected value in each of these models. So last part, comment on the comparison of the answer in part 6 taking into account your answer in part 5. The expected sale amount is exactly the same using both the models from part 5. The gamma model was slightly better than the normal model. Hence gamma model should be used. Although normal model can be used for simplicity as the difference is negligible. That completes our paper here. So the questions were very straightforward, but they gave you a lot of comments. So you might have spent a lot of time just thinking what to comment on it, and you might have felt that the paper was lengthy. They had 4 questions related to correlation, linear modeling and GLM. So if you did not prepare those topics well, you might have faced a lot of problems here. But if you were well prepared, you might have felt the paper was very straightforward, very simple and fairly lengthy. Overall, I felt the paper was fairly simple, so the passing marks will definitely go high, maybe around 57, 58 or up to 60. If you find any mistakes in my solution, do let me know in the comments. I'll try to reply as soon as possible. If you find the video helpful, do like and share with others. I've already made the paper A video. If you have not checked that out, I will leave a link in the description. To get more videos related to actual science, do subscribe to my channel and I'll see you in the next one.